It's fun to introduce Sreerup Raychaudhuri to the audience in case you don't know who he is. Currently, of course, he's a professor at TIFR, but he started off his career studying at the University of Calcutta. And then he also completed his PhD at the University of Calcutta under the supervision of ARC. And the interesting thing is that even during that time, he spent time in TIFR, and it's like TIFR was like a fixed point or something in his trajectory in life. So he would keep coming back to TIFR. So after he finished his PhD, he was a postdoc at TIFR, where we both were there postdocs at the same time. So that's when I got to know him well. After that, he went to CERN and eventually went to IIT Kanpur as a faculty member. And then after a few years there, he returned to TIFR as a faculty member, and he's been there for a long time now. And a few interesting things about Sreerup is that he knows a lot more than physics. He's an expert on many other things, and it's kind of intimidating once you see that his knowledge on various things like history, mythology, and so on and so forth. But he also loves teaching, like me. He also loves teaching, and so I think he's probably looking forward to giving this talk. So with no more introduction, here's Sreerup.
Okay, thanks, Suresh, for that very warm introduction. And actually, I have joined TIFR 3 times, which is a record. No one else has. So once I joined as a postdoc, once I joined as a visiting scientist after I came back from CERN, that was for 6 months. And then I joined as a faculty member again. So I think that's a record which no one else has. But anyway, let's get down to the business of today. So this lecture is about Lie groups and gauge theories in particle physics. So gauge theories are sort of indistinguishable from Lie groups where particle physics is concerned. And this is probably also one of the root causes why Harish Chandra did get interested initially in Lie groups. So let's start with a very introductory slide. Is it moving? Hello. Moving. So just how do I get rid? Okay. So I start by just reminding you that in this entire lecture, I will use the so-called natural units. So since we are going to use both relativity and quantum mechanics, it's convenient to set C equals 1 and H bar equals 1. So that results in some dimensions being the same. If you put these are dimensional full quantities which you put to something without a dimension. So length, time have the same dimension. That's inverse of mass and inverse of energy. So everything is written in units of energy. This is so that's right. So that you will not see any factors of C and H bar in what I write. So let me very quickly revise the formalism in which we are going to work is that of a Lagrangian field theory. So let's have a Minkowski space with coordinates x, and the psi of x is a field defined on that space, which means that for every value of x, there's a value of psi of x. So there's psi of x, at x prime, there's a psi of x prime, and so on. So this is a one-dimensional system. Now, if you treat the psi of x at every point as a generalized coordinate system, then this is a system with an infinite number of degrees of freedom. So, I mean, this is a coordinate, this is a coordinate. At every point, you have a coordinate. And in Lagrangian dynamics, this will be described by a Lagrangian. So the Lagrangian will be a function, some function, it's called the Lagrangian density of all of these coordinates and their derivatives. So like in Lagrangian dynamics, you have the time derivatives, but here, because it's relativistic, you'll have to have the space derivatives also. So all the derivatives. So mu goes from 0, 1, 2, 3 in relativity. And it's, of course, summed over all the points in space, so all the coordinates, so integrated over the space. And action, of course, means there's an additional integration over time. So it's a 4-dimensional integral of this Lagrangian. Now, the dynamics, of course, follows the Hamilton principle of extreme action, that if psi changes by some quantity that is extremal, then delta S is extremal. So delta, there's no change in the, it's reached a maximum or a minimum. So this, of course, if you go through, it will lead to the Euler-Lagrange equations. And this is how they look. Change in the Lagrangian density, derivative with respect to the 4 derivative of psi, and 4 derivative of that, and minus del L del psi. If there are many fields, not one side, then the Lagrangian will have all those fields and all their derivatives, and there are n sets of all the Lagrange equations. We just put I. The action integral will now be four-dimensional over all of these, and all the Lagrange equation, of course, will just have an I with each of these. So psi 1, psi 2, there'll be so many all Lagrange equations. Okay, so what are the kinds of typical fields which you need to work with, at least for what we are going to do? The real scalar field. So this is the Euler-Lagrange equation. It's also called the Klein-Gordon equation. And this is the form of the Lagrangian density. So it has del mu phi, it has phi. Then if it's a complex scalar, of course, there is phi and phi star are two coordinates. Same equation satisfy that. And this is how how it looks. Then we also have Dirac spinors. So for Dirac spinors, this is the Dirac equation. This is the Dirac adjoint spinor. So these are the two coordinates. And the Lagrangian is like this. Finally, the electromagnetic field. These are, of course, the famous Maxwell equations. And there is, of course, one more constraint equation on them, where F nu is defined in terms of the electromagnetic field. And you have because it's sort of central to what is done. So if under a transformation, we change all the coordinates by something and still the Lagrangian doesn't change. Okay. That's the simplest form. This will be called a symmetry of the system. Now, for an infinitesimal change, of course, the Lagrangian will depend on all the coordinates. So the delta size and the delta of the del mu size and summed over all the size. Now, the point is we have the Euler-Lagrange equation. So this del L del psi I can be substituted by this del mu del psi I. This is what I had on the previous page. So if you make that substitution, I made it here. I've written this del mu del psi, this term as it is. And the second term has this del mu del psi I with the delta psi I. But if you look at this, you see that this is a total derivative. You have this term, derivative of delta psi, the derivative of this big term and delta psi. So it's the derivative of this product. And that means that if delta L is and I can pull the del mu outside. So it's the derivative over some quantity, which I call del J mu. And J mu is called the Noether current. And the delta L is del mu of J mu. Now, if this is a symmetry, delta L is 0. So del mu J mu, which is the 4 divergence, is 0. So for symmetry, you get this, and that's, of course, an equation of continuity. If you write it out explicitly, the equation of continuity, del mu J mu, is the time part, the space part, and integrating over all space, the time part, integral space part. The space part becomes a surface integral, which vanishes because as you fields vanish over the surface. So whatever is the time integral of the zero component is constant with respect to time, and this is called the Noether charge. Okay, now we will talk about a specific kind of symmetry, and that is called a gauge symmetry. So to look at this Lagrangian density, this is Lagrangian density for a single charge scalar of mass m. So the Klein-Gordon equation of box plus m squared of phi and box plus m squared of phi squared. These are both 0. Now, if you make what I call a global gauge transformation, which is nothing but a change of phase of phi, what happens? You get e to the ig theta here, you'll get e to the plus ig theta here. So they'll cancel. You get e to the I minus ig theta here. Because these are constants, it will come through the derivative and it will hit the e to the plus ig theta here. So you get, it comes out of both. So therefore, it's manifestly invariant. And here, theta is an arbitrary constant. So different values of theta can be different transformations. G is a sort of bookkeeping constant. It's specific to the field. So, for example, if G is 0, the field doesn't transform. And if G is non-zero, and it could be 1, 2, 3, depending on that, we'll see what the meaning of G is shortly. But it's a constant specific to the field. Now, we could also write this, of course, in real form. This phi of x, we could write as phi 1x plus phi 2x, and so on. If you do that, then this transformation would be in this form. So this is nothing but a rotation in the complex plane, which, of course, we know that changing the phase of a complex number is like a rotation in the complex plane. So this is actually also an O2, it's an SO2, it's an SO2 rotation if you use the phi 1 and phi 2 as fields. Now, rid of this, some way I can unsend. I can hide this panel somewhere, right? Ah. Okay, so now I can't see what it is. Can someone read it out to me, what this says? I mean, I have some box sitting on top of this.
Yes,
Okay,
you're on the slide.
yeah. Okay, so this set of transformations forms an abelian group. Okay, now let's see that very quickly. So for a group, we have to see that successive transformations are, of course, one after the other. So this is so clearly this is one theta. So it's you have closure. Associative because you have a sum here, so sum is associative. So therefore, if you take theta equal to 0, you get into the zeros, you get the identity. If you take minus the opposite side, you will get into the zeros, so the inverse is there. And of course, there's an addition here. So that addition is, of course, commutative. So this forms a set of group of unitary 1 into 1 matrices, which is called U1. And these are called global U1 gauge transformations. Why global? Because G and theta are constants, it's the same at all points in space and time. So it's a global transformation, occurs over the whole of space and time with the same phase. And they are global U1. Okay. Now let's quickly find out the Noether current. We've learned how to find the Noether current. That's my Noether current, del L del J mu. So if L has this form, then del L J mu is del mu phi star, and del L del mu phi star is del mu phi. And if you take an infinitesimal gauge transformation where theta is very small, so delta phi is phi prime minus phi, of course. So you make this transformation, expand the exponential, keep only the linear term. So we have got the delta phi's also. And then if you plug in these values, what happens? Remember, we plug in del mu phi star, del mu phi, and then we plug these things here. So you get del mu phi star into this, and del mu phi into this. So you can pull minus I d theta. So theta is the variable parameter. And you get del mu phi star phi minus phi star. Now, of course, the theta factor is arbitrary. But if the derivative of this is 0 and theta is just a constant, so the derivative of the rest will also be 0. So this is my scalar current, and it's often written in this shorthand notation with del mu arrow going both ways, which means that once the derivative acts on this fellow, and once it acts on this fellow. So once it acts here, once it acts here. So that's what we call the scalar current. And the Noether charge, you just you take the time component and integrate it over all space. And then you get this what is inside is nothing but the probability for a Klein-Gordon particle. Total probability. Now, gauge symmetry, of course, obviously then leads to conservation of this quantity. So conservation of probability. Moreover, if the field is normalized, this integral is 1, and therefore the Noether charge is Q. So therefore, now we understand what G is. G is just the charge. It's the Noether charge corresponding to this field. So different fields will have different Noether charges, and that will be the charge under the gauge charge of the field. Okay, now we have a slightly tricky issue is that a global gauge transformation is not compatible with relativity. Why? Because it assumes that the transformation which will happen at x and at x prime will happen simultaneously. And that's not possible because, of course, signals will take a finite time to propagate. They can't go faster than the speed of light. So therefore, the theta which you will get here, so when this theta happens, this thing will still be 0. And it will change as time goes. So it is better to replace this with a local transformation. So with the local transformation now, this also forms a U1 group, no question about that. And of course, mathematically, the set of U1 transformations is a subset of the local ones. So constant is a subset of functions. So therefore, that also is there. But if the global gauge transformation is difficult to interpret physically. So now we should demand that the action should be invariant under this transformation. That means the local transformation, since it is physically meaningful. So if you put in this demand, let's see what happens. Under the local gauge transformation, the fields will change by exponential, by these phase factors. The Lagrangian changes, let's say, there's derivatives here. So when the derivatives act, they give us two terms. Look at this del mu here. It will act first on this term and give me a del mu theta term. Then it will act on the phi term. So if you, put everything together, what you get is the original Lagrangian with the del mu phi's. And then there are these two extra terms, the del mu theta term and there's a del mu theta term. So therefore, this theory is no longer gauge invariant. Now, this is not physically acceptable because if the theory is not gauge invariant, then we should be able to measure the phases of the wave function. And that we cannot. So that's a paradox. And whenever you have a paradox like this, it means that your theory is incomplete. There is something which we have missed out. So what is that? So there must be some other field present, always present if there's a gauge transformation. And that we have missed out. So let's try to find that. So we take this Lagrangian density, we replace these derivatives by derivative term plus a term where we multiply by a field A. And we make the transformation of mu such that it makes the thing gauge invariant again. So we're adding this, and under local U1 gauge transformation, what happens? Del mu phi plus will go to del mu phi prime, a mu prime, which I don't know what a mu prime is, and phi prime. So I'm just taking the substituting for phi prime everywhere. Now I will get the derivative terms here. So I can rearrange these in the following way. I can put in e to the minus ig derivative, and then there are these two terms. One of which has del mu theta, which comes from the fact that the transformation is local. And there's an a mu prime, which I don't know. So I could also write it like this, as just recollect the terms, del mu theta minus a. Now, if I want the, under local, if I want this to just give me del mu phi, I want this thing to be 0. So if we make this to be to 0, then a mu prime is equal to a mu plus del mu theta. So if we allow, say, this is the transformation law for the a mu, then I will get back precisely this. So then in this Lagrangian here, so this one will become an e to the minus ig theta term. This one with the star will become e to the plus ig theta, and again everything will be invariant. So if we make this field A, which is the gauge field, transform in this fashion as a mu plus del mu theta, then the local gauge invariance is preserved. Shorter notation, this whole thing, let's write it like this in terms of a capital D mu. So with the del mu plus ig mu, we just write as capital D mu. The Lagrangian density becomes d mu phi instead of del mu phi. And we have seen what happens, that phi transforms as e to the n. And the d mu phi, which is this object, transforms in the same factor outside. And so now, of course, the Lagrangian becomes trivially gauge invariant. Okay, you also notice that the d mu phi transforms in exactly the same way as the phi itself. So we call it a covariant derivative. Now, this is exactly analogous to the case of Riemannian geometry, where we add an affine connection to the derivative to obtain a covariant derivative. And we also know that Einstein exploited this by saying that space-time is a Riemannian space, and this connection eventually leads to the gravitational force. That's the theory of general relativity. So there's a force involved in this extra term in d mu. And we'll see the same thing that will happen for gauge theory. So let's write out the Lagrangian density in full. So this is the term, and I have just multiplied out all the terms. And so you see there'll be del mu phi into phi star. Okay. Del mu phi star, then the phi and a mu. So all the terms will be out. Now, what I can do is this term here, this is nothing but my Noether current. So that's the Noether current. So if you look at the first part, this is just the free Lagrangian before I had any gauge field in it. So this is the Lagrangian for a free scalar. Here is a term which looks like G times J mu A. So this is like a detection. This term has a special form. It is like the product of two scalars and two gauge fields. It's called a Seagal term. Now, do we understand this a mu field? So let us do something. Let's take the Euler-Lagrangian equation for this a mu field. So if you work it out, then this is the Euler-Lagrange equation. Then a nu, you get this Euler-Lagrange equation. You just take the derivative from this Lagrangian. You get this Euler-Lagrange equation, and a nu becomes j nu, so it can be written entirely in terms of the scalar field. Now, if that is true, and I take this function and I plug it into the mu here and here, I will get a nonlinear Lagrangian. So the wave equation will also be nonlinear in phi. And with nonlinear wave equations, we cannot quantize it. So you can't do a quantum. So have we missed something? Yes. So what have we missed? So the mu should be an independent field. And to do that, it must have some dynamics. That means there must be a term with del mu in. See, if we go back to the Euler-Lagrange, it was just an algebraic equation, because in this equation, this whole term vanished. This del mu term vanished. I had only del L del N. So in that case, that's what we call an ignorable coordinate. So therefore, we don't want it to be that. So there must be a term with del mu in. Now, how do you introduce a term with del? So this term has to be both Lorentz invariant and gauge invariant, because the Lagrangian has to have both these invariances. Now, see, under local gauge transformation, we know that nu goes to nu plus del nu theta. So del mu nu will go to del mu nu plus del nu theta, and then del nu nu will go to del nu nu plus the same thing. Now, these two are the same, we know that. So it will cancel. If you take the derivative difference, it will cancel. So the f mu nu, which is del mu nu minus del nu nu, will remain invariant. This quantity is called the field strength tensor. And of course, if you multiply two of them, this is Lorentz invariant because of the contraction of indices. So the full Lagrangian, what we do is we add this to the Lagrangian with a minus 1/4, which is for bookkeeping. And what will happen is that if you take the Euler Lagrangian, it will look like this. Now, if we didn't have this -4, you would get a -4g. So just to get rid of that, we kept that constant. Now for small g, this reduces to just g. So forget about the g squared term for the moment. You'll get del mu f mu, which is g nu, and that is identical with Maxwell's equations. So it follows that this mu must be the electromagnetic field, and this g must be the electric charge times whatever is the fractional charge of the particle. So plus minus, +1 for -1 for electron, +1 for proton, 2/3 for quarks, and so on. So now the important thing we have come up with is the quantum mechanics of a complex scalar field. Quantum mechanics, because we wanted linearity, has no physical meaning unless we couple it to this electromagnetic field. So all electromagnetic phenomena are ultimately linked to the fact the gauge invariance, our inability to measure the phase of a wave function. Okay, so in a sense, the same thing happens in general relativity. The gravitational field, we may say, arises from the fact of our inability to distinguish between accelerated frames of reference. So if we say that all accelerated frames of reference give the same rules, that means there has to be a gravitational field. Similarly, if the wave function, all phases of the wave function give us the same probability, then there has to be an electromagnetic field. It comes from quantum mechanics. All right, now let's just look at the Dirac field. We've looked at the scalar field. The Dirac field is even simpler. Here is my Dirac Lagrangian. The Dirac field transforms in a similar way under IE. So I now put E as the charge. That's the Noether charge. You can easily show that the Noether current is just E times psi bar gamma mu psi. And the Noether charge, if you go through it, gives you this integral of psi dagger psi, which is the probability. And that gives you E. So it is very similar. And then for local gauge invariance, you replace this. You replace this d mu by a del mu by a d mu, just as I had done elsewhere. Whereas before, the d mu is del mu plus I mu, f mu is as before. Expanding the covariant derivative, you get this. So now, okay, so I just rearrange the terms. You get a free fermion term. You get your free electromagnetic field, and here is the interaction term, which is of the form J mu n. And your Maxwell equation will be del mu f with E. So there is no Seagull term here. Partly because of dimensions, and just it didn't come in the Lagrangian. So of course, now we know why we got Maxwell's equation like this, because the electron is a Dirac fermion, and Maxwell equation came from doing experiments with electricity magnetism, which is all with flow of electrons. So Maxwell's equations arise from a Dirac fermion. So that's why that Seagull term didn't come. But if there was a scalar, charge scalar, then we would have seen that Seagull term. The Seagull term is going to play a very important role in what follows. So it is necessary to worry about it. So this, of course, is the theory of quantum electrodynamics. Okay. Now, once we have Maxwell's equations, you can write this out explicitly. So the del mu F mu is del mu of this. This is the definition of F mu. So this is del mu, which is the box operator, minus del mu of del mu. So box minus del mu of this. Now, if you choose the Lorentz gauge where this thing is vanishes, you get 0, you recover this equation. Now, this, of course, is the four-dimensional Poisson equation. So in the static limit, the 0 component will go away. So in the static limit, okay, the 0 will be there, of A will be there, but the box will not have any time derivative. So it will become minus of Laplacian. So you can write Laplacian of A nu is equal to minus E times A nu. And that, of course, is the Poisson equation. At least for the 0 component is the Poisson equation, which is the same as Coulomb's law. And you know that leads to a 1/r interaction. So it's a Lorentz interaction. Now let's ask the question that could the photon have a mass? I mean, can we associate a mass with the electromagnetic field, AD? So suppose the Klein-Gordon equation would then be box plus m gamma squared. And the Maxwell equation would then have to have an m gamma squared AD term in it. Okay. All right. So if this is the Lagrangian density must have an extra term of the form A nu. Because when you take the derivative with respect to A nu, you should get the other A nu back. And there are two possibilities here. So that gives you a factor of 2. So you'll have this extra mass term. Now the problem is that under a gauge transformation, the A nu picks up a del nu theta. So you will have this. And clearly there are 4 terms here, out of which only the first term is what we had. And there are new theta dependent terms. So this is not gauge invariant. So to have gauge invariant, you will have to set m gamma to 0. This term cannot appear. And so the photon must be massless. So we can also argue that photon massless is the same as that Poisson equation. So therefore, gauge invariance leads to long-range interactions. So long-range interactions come from gauge invariance. So therefore, it's fine for electromagnetic theory. But when we look at nuclear interactions or more interactions at the elementary particle level, then the weak interactions and the strong interactions cannot be of this kind. Or can they? We'll have to see. All right, we have just seen this. Now the question is that even the electromagnetic interaction is not always a long-range interaction. And where is it not long-range? It is inside a superconductor. Now what happens in a superconductor? At a temperature below the critical temperature, it exhibits the following behavior. It is a perfect conductor, which means that there is no electric field, it's thrown out. That was discovered by Camille-Leonis. And it's also a perfect diamagnet, which means the magnetic field is also thrown out. And this was discovered by Meissner and Oxford. So that means that both the electric and magnetic fields are thrown out. That means no component of the electromagnetic field can propagate inside a superconductor. It's a region which is totally shielded from the electromagnetic field. Now, of course, nothing happens in nature happens abruptly. So at the edges, what happens? There is field outside. Field is 0 inside, but it doesn't go like a step function. It falls off exponentially. Exponential fall is a very rapid fall. And that rapid fall is governed by some length, L, which is generally known as the penetration depth. In superconductor theory, there's penetration depth, and people measure that in the lab all the time. It's a very small length. It is maybe some tens of microns, hundreds of microns. So if you have a superconducting sample, effectively the bulk of it is free of fields. But at the surface, there is a little bit. Now, so here, so if fields fall off like this, if the mu falls off like this, now that is a solution corresponding to the massive Klein-Gordon equation. And therefore, this is the same as E being minus m of x, where m is 1/L, is the mass. So effectively, inside the superconductor, the photon has picked up a mass m, which is 1/L, L being a measurable quantity. So, okay, I'm just written that photon is massive inside a superconductor. So somehow this local U1 gauge symmetry, which was protecting the mass, okay, keeping the photon massless, this local U1 gauge symmetry must be breaking down inside the superconductor. So it's something strange, right? It breaks down below this temperature, critical temperature, but above the critical temperature, no, it comes back. It comes back, the symmetry is back, the photon again becomes massless, and fields again flow into the superconductor. So do we understand this phenomenon? Actually, we do. It was first explained by Landau and Ginzburg in 1937 for a non-relativistic theory, which is what actually applies to superconductors. It was extensively applied in condensed matter systems with plasmons and so on by Philip Anderson in the 1950s. And it was worked out for a relativistic theory by Ongley and Brout in 1964, independently by Peter Higgs in 1964, and also by another group, whom I will show you at the end. This phenomenon is called spontaneous symmetry breaking, but a better name given by Coleman is hidden symmetry, and we'll see why. So, the hidden symmetry, which I'm going to talk about now, this arises when the action of a system has a particular symmetry. As we have just seen, we have looked at the action having U1 gauge symmetry, but the ground state does not obey that symmetry. Now, how is that possible? So, I'll give you a sort of fun example, and then I'll give you a more serious physics-like example. So the fun example is Salam's banquet. So this is an example Salam gave in his Nobel lecture. So imagine people are sitting down to dinner at a round table. Okay. So here is a sketch of the table, round table. Each guy has a plate, and there are chairs all around. And there's a glass. So there's a glass in between the plates, each of the plates. Now, when you sit at a particular plate at this place, you have a glass on your right side and a glass on your left side. There's a glass of water or champagne or whatever you want. So before that, you can either pick up your left glass or your right glass. There is perfect symmetry. However, the first person to pick up a glass, he makes a random choice. Say he picks up the left glass with his left hand. But now this fellow has picked up the left glass. So the next guy has no choice except to pick up his left glass because his right glass is taken, and so on around the table. So everyone must pick up the left glass. You have probably, if you've sat in a row to eat somewhere, you must have seen this phenomenon. So now that everyone has to pick up the left glass, so if I come in the middle of the meal to see what is happening at the table, I don't see any symmetry. There is no symmetry between everyone is using the left glass. So that's it, no symmetry at all. However, has the symmetry disappeared or has it been destroyed? No. See, if you consider not just one table, but a whole bunch of tables, like a wedding or something, many tables, everyone is sitting down to the banquet. All these tables have the same identical structure, but in one of them, let us say, somebody picked up a left glass and one of them picked up a right glass. So what is the probability? The probability is that half the people will pick up the left glass and half the people will pick up the right glass. So that symmetry between left and right has now moved from the individual table to the ensemble of tables or to the ensemble of systems. So what has happened is that it has become hidden from one single system, but it has reappeared on the ensemble. So this is why symmetry is there. So this is why it's called a hidden symmetry. Okay, so now I will give you a more physics-like example. Look at a ferromagnet below the Curie temperature. So above the Curie temperature, what do we know? That all the domains are in random directions. So there is rotation invariance. This is the Hamiltonian, Heisenberg Hamiltonian. We have a dot product here. So it obeys rotation invariance. So all directions are the same. But once you go below the Curie temperature, all the domains have been aligned to a particular direction. So if you are a little fellow sitting inside and you make a measurement of the magnetic field, you will find a preferred direction and say, okay, there is no rotation invariance. That particular direction is favored. It's special. However, if you consider a bunch of ferromagnets, then the domains will sort of crystallize or in different directions. So if you look at if you take an opinion poll of all of these guys, then in that opinion poll, you will find that all directions are there. Okay, so the symmetry has reappeared. However, the point is that if you are confined, so the Coleman imagines a little fellow like Maxwell's demon, which is known as Coleman's demon, who sits inside a ferromagnet. So to that fellow, the rotation invariance is always violated. He doesn't know that in other systems there are other things, and if you look at the ensemble, it is there. And you see that this is always associated with a phase transition. So at a high temperature, the symmetry exists. At a low temperature, the symmetry disappears. In between, this flip occurs, which is called the critical temperature. And that's the Curie temperature in this case. And superconductivity is the superconducting phase temperature. So how can we get that in superconductivity? We discussed the relativistic model. Of course, the actual to an actual superconductors are mostly non-relativistic. So, but we will apply the relativistic model to particle physics. So let's do that. So imagine that the interior of the superconductor has, in addition to the electrometer, there's a charged scalar field. And of course, there's an understanding of this charged scalar field. It can be the field of Cooper pairs, which is a scalar, which are scalars. So imagine that that effective field theory of that is a charged scalar is everywhere smeared out inside the superconductor. And we have already seen that this leads to this kind of Lagrangian density. Now, in addition, let that scalar field have a self-interaction term. So I've added so this is phi star phi is a mass term. I've added a phi star phi whole square term. So if you add this term, then it will be like a phi extra term, and these are called interaction terms. And because it's only phi interacting with itself, it's a self-interaction term. So now you see this, forget about the F, this is like a kinetic term for phi, and this is like a potential. So you can take these two terms and think of them as a potential. So I can write this as W phi minus potential, and here's the form of the potential.
Is a question or a doubt or remark in the chat box?
Sorry, I can't see the chat box, but let me see now.
You can read it also.
Yes. So Ashwini, I will come to this shortly. Okay. Right. See, in our universe, of course, but for a ferromagnet, of course, you can have several magnets. Okay. You can set out 100 magnets on a table, one after the other. But universe, of course, we have only one universe, and I will come to this point. So thank you. Okay. So now we are talking about this potential. So you write it like this. So it's m squared phi squared plus lambda phi fourth. Now, if you plot this function as a part of phi, what will this look like? This is a parabola, this goes up even sharper. So the minimum is at mod phi equal to 0. So this is perfectly symmetrical. So go around phi. So imagine, so this is phi, this is mod phi. So if you have a phase, then you can imagine this rotating about this axis. So what you will get is a sort of, a sort of bowl. A bowl with a minimum at the bottom. So only one unique minimum, no symmetry there. Entire rotation symmetry is there. However, suppose you consider a variant of the theory where you change this sign. Okay. Remember, I have here minus m squared. Okay. Now I make this plus m squared. So what does that mean? Of course, you can't treat now m squared as a mass anymore, because this is like minus of im squared. So the scalar particle will have an imaginary mass, it will become, but we don't want to say that. Just let this m squared be another interaction term. So these are two interaction terms, and the whole thing is a potential. But now at this potential, there is a minus m squared. So now if you take the extrema, where will they lie? You can just work it out. They'll be at phi equal to 0. And then there are these two values, m squared by 2 lambda, where you have minimum. Let me just see if I remember this. So these are the minimum. You can just work it out by, and these we will call v by root 2. There's a 1 by root 2, so m squared by lambda, or m by root lambda is called v. It's just a convention. So what is actually happening? So this is how the potential behaves. So you see, you have this minus m squared phi squared. So this is an inverted parabola, right? Now, as when phi is small, this term dominates, the phi fourth term is small. As phi increases, this term begins to contribute more and more, and it's on the positive side, so it will drag the potential to the positive side. So here you have this sort of inverted parabola in the beginning, and then as the phi fourth increases, it just pulls the thing to positive values. So you have this shape, and this is sometimes called a Mexican hand, but the easiest thing to think of the bottom of a bottle. A glass bottle typically has a bottom like this. And if you have a glass bottle or even a water bottle in front of you, you can just see it, right? And see all the entire circle at the bottom. All of these can be the ground state. Anyone can be the ground state. So like in a ferromagnet, all the directions can be the ground state. Or in slug bracket, either right glasses or left glasses can be the ground state. Here, any of these directions can be the ground state. But what happens in nature? Only one is the ground state. Just like in the ferromagnet, only one direction is the ground state. So when that one direction becomes the ground state here, then of course the moment that one direction becomes the ground state, the symmetry becomes hidden. Only one direction being chosen means the symmetry immediately jumps out from the individual system to the ensemble. So let us orient the axes. So this is just a convenient parameter. So if this is the axis, we just rotate the axis and choose the axis such that this is the real direction. I mean, this is nothing. Suppose you do this all the time. Like if you have a constant magnetic field, you choose your z-axis along that to make your formula simple. So we'll do that. So now the ground state is phi naught is v by root 2. Now, of course, if you want to have a field theory, it had better be around the minimum. Field theory should be expanded about the minimum, only then you can break it into small oscillators or whatever and do path integrals. Only if it is around the minimum, not around. So the field theory you have is around this maximum. So that is unstable. So to do that, you have to move your phi to phi naught plus phi prime, and phi prime is, so phi prime is your new field and phi naught is this constant. So expand around the ground state, rewrite the Lagrangian density in terms of this, calculate the terms one by one. So I've done that here. The d mu phi will have three terms. Of course, the d mu of phi naught will be 0, del mu of phi naught, because it's a constant. We have del mu phi prime, there's an e phi term, and there's a phi naught a term, e phi naught, a term which is only the a field, a term which is the a and the phi prime field and the derivative field. So it follows that when I take this product together, I will have the three terms here. The d mu term, the mu and product of the two terms, and only the mu term. Similarly here. All right, but now, okay, all I have done here is I have taken the star and taken the star inside. Now, if you look at these two terms, these last two terms, there's one mu here, there's one mu here. Rest are constants. So this will give you what you have here, minus I plus I. So let's go away. E squared, phi naught squared, mu. So this E squared, phi naught squared is a mass. Right? So I've generated a mass term for the mu. So if you recall this, then you can compare these two terms, half m gamma squared, E squared, phi naught squared. So m gamma is root 2 E phi naught, root 2 E to V by root 2, so E times V. So inside the superconductor with this potential, when you go close to the ground state, the photon becomes massive. All right. And of course, this mass is a manifestation of the scalar self-interaction because lambda is there. Okay, if you didn't have lambda, this would not work. But now, so what is the argument? That go back to this potential. So when are you near the ground state? When you are at low temperature. So at low temperatures, the superconductor behaves like that. Then when you come up to this temperature, then you have crossed the threshold where you see this entire, otherwise you see only this neighborhood. You see this entire, potential, and then that is the critical temperature. So the superconductivity has gone. So the superconductivity comes only at the low temperature because the ground state breaks the symmetry. So that is the very beautiful idea. That you can have a symmetry, you can also have something breaking the symmetry, provided you're close to the ground state. Another miracle which happens is that, see, this was my m squared. So I have moved the phi's. And I have moved the phi. So this was my potential. Remember, I had only phi, but now I have moved the phi's to phi naught plus lambda. So if you multiply these out, what you will get is several terms will cancel, and you can work out the details. So you will now get, so because phi naught squared is m squared by 2 lambda, that's the vacuum exchange value. It follows that V of phi, now see, these are, this term will become 0. This term will vanish. M squared by 2 lambda. So 2 lambda phi naught squared is just m squared. So this term vanishes. But you will, and so this real part imaginary will go away, but the real part of phi whole square will come with a term like this. And look at the sign. You started with the negative sign, but this term has a positive sign. So in the potential, this is a positive sign, which means that this is a real mass. So your U1 symmetry, of course, is broken, and your phi prime, which is the symmetry between phi. So phi prime is only the real part. So the real part, imaginary part, means, of course, your U1 symmetry is broken. So now you can't have a phase symmetry anymore. But here is your mass. And so this has a real mass 2m. So this 5 scalar field now has a real mass. However, the imaginary part of phi is massless. Okay, the imaginary part of phi went away. When this term became 0, the imaginary part went away. So the imaginary part is massless, and you have what is called a Goldstone boson. In fact, Goldstone proved that for every spontaneous broken continuous global symmetry, there corresponds a massless boson. So these are known as Goldstone bosons. Now, how to get rid of this massless boson? Because if we did have a massless boson, there would be new long-range interactions, which you don't have.
Message, sir.
Sorry?
There's another message in the chat.
Okay.
Chat box.
Yes, we will have a mass gap. The answer is yes. We will have a mass gap. And no, M, I had mentioned that in that Lagrangian, M is not the mass. Before you break the symmetry, it's an interaction term. But after you break the symmetry, it has become a symmetry, a mass term, and you will have a mass gap. So there was no mass gap when you started the theory. You started with at high temperature. But when you went below the critical temperature, close to the ground state, then a mass gap appears. Okay, so now, but of course, we are also left with this other term, which doesn't have a mass gap. And we can't live with that because it would give us long-range interactions. So to get rid of that, now this is the beautiful work done by Ongle and Brout and by Higgs. They can be done if it is a local symmetry. How do you do that? It's very simple. So, you use hindsight. You parameterize your phi in a polar form, which you can always do in terms of two fields, and consider the unbroken gauge Lagrangian density with this potential, and you rewrite it in this. So at this stage, of course, you have gauge invariance. Okay, even though you have the wrong sign here, but you have gauge invariance. So if you have gauge invariance, you can make a gauge transformation. So let's make that gauge transformation. So phi of x, we make the gauge transformation. And since you know that you're going to break the gauge, you might as well choose a special gauge, because at the end of the day, you will need a special gauge. So this is just like you have rotation symmetry. You choose a particular direction. You're going to have switch on a magnetic field. Suppose you imagine that you know beforehand that you know the direction of the magnetic field. Okay, make your coordinates such that they point along that magnetic field, so that as soon as the magnetic field comes on, the x and y components are 0. They don't exist anymore. It's something like that. You choose your gauge, you choose your psi, which is your gauge transformation, such that this thing becomes 0. So in that case, phi x becomes only eta x. Okay, this is called the unitary gauge. And in this case, you have this, the Lagrangian has this very simple form. Still, you have a potential with the wrong sign. But when you go through all of this, you still have to shift. And eventually now what you will have is the mass term will come with it. This is EV. You will have the proper sign for phi prime. This will come with that. And there is no Goldstone boson. So all these three good things happen. If you had kept the psi, it would have been the Goldstone boson. Now, of course, this looks like magic. How can a degree of freedom of the system disappear? Okay. And actually, you see, it hasn't disappeared. In the unity gauge, you see, the photon has become massive. A massless photon has only transverse direction. It has two polarizations. A massive photon has a third degree of polarization. So what has happened is we have reparameterized our fields in such a way that the longitudinal polarization of the photon is replacing the Goldstone degree of freedom. So the number of degrees of freedom remains the same. It has just moved. It has just been reparameterized in a different fashion. And this is known as the Higgs boson. So effectively, you say that the photon has swallowed up the Goldstone boson and become massive. And the classic example given is you see the snake. And it doesn't look much like a snake, does it? It's not long and thin like a snake, but it's looking like this because it has swallowed up that egg. And while it's swallowing it, it looks like that. So this is the analogy. The photon has become like that. The long, thin photon has swallowed up this Goldstone boson and it has become massive. All right, so that's essentially the end of the lecture. Let me introduce you to the people who came up with these ideas. So the first paper written on this was by Robert Brout and Francois Anglais. So Anglais is still with us. That's why a color photo. And almost immediately after that by Peter Higgs. Okay, now we lost Higgs only earlier this year. And then a little later in that year, but there was no archive in those days. So people didn't know about other people's work so fast. Same job was done by Guralnik, Hegel, and Tom Kibble, of whom only Hegel is still alive. The rest have passed on. And as you know that after the discovery of the Higgs boson, so which is the Higgs boson? This one. This eta is the Higgs boson. And of course, this is U1 theory in the standard model. So after that discovery, the Nobel Prize went to Francois Anglais and Peter Higgs. Robert Brout, unfortunately, this when the Higgs discovery happened in 2012. He had passed away 1 year before that. And these people's paper came about 2 months later, so they missed the bus, rather unfortunately. But anyway, that's the way things are. So right now, Higgs is also passed on, so Anglais is the only Nobel laureate for this. Okay, that brings me to the end of my lectures. So for today. Next day, I will take up the same thing with the non-abelian case theory. So with the non-abelian group today with you. So open for questions.
Yeah, thank you, Sreerup. There were a couple of people who asked questions. Can they ask it again if you have not answered it?
Yeah. Sorry, if they are they in the chat or?
Yeah.
Yeah, so, okay. So the first is of the ensemble of possibilities, only one of them is realized in our universe. So I haven't gone to the universe yet, right? So today I'm still talking about ferromagnets and superconductors, of which you can easily build an ensemble. Okay. However, when we talk about electroweak symmetry breaking, of course, there is only one universe. So we are in the position of Coleman's demon. We are sitting inside one ferromagnet or sitting inside one superconductor, and we cannot see the fact. But if we could have had an ensemble of universes, or if an ensemble of universes exists, then we would see other phases in the other universes. So that's the answer to this. The answer is yes. One of them is realized in the universe, yes. And the second question, I think I've already answered that, you don't change the sign of M. What happens is that at low energies, the effective field has the opposite sign of M. So the mass gap appears for that effective field, for the shifted field. So there is no mass gap for the field if you keep it, centered on the origin. And that's what you will do if there is high energy and you can neglect all that stuff at the bottom. But when you are close to the ground state, which means at low temperatures, then that you get a different field. The effective field is the shifted field, and that field has a mass gap. So the mass gap is generated at that point. Yeah. So any.
Sir, can I ask one question?
Sure.
Sir, you showed that the generator of the U1 group was related to neither charge somehow.
Yeah.
How does the generator of the group is related to the any charge, like for a continuous symmetry? How is it related? Is it a general statement?
No, it's only true for one. There is some relation. Okay, there will be generators of charges. So, okay, the point is, how do you define a charge? Okay, it will not. Okay, generators. Let me put it like this: there will be currents, not quite charges, and there will be some charges, but generally the group symmetry is realized not on the charge. This is U1, that's why it's run on the charge. It's realized on the currents. Okay, so I'll do an example of that with SU2 next day.
So for SE2 also the neither charge are the generators
They will
of
be
the
there, but the group symmetry is realized on the current. The currents become the generators of the group symmetry, not the charges. So we'll see that. I mean, to generate, I mean, if you have to be generator of the group symmetry, you have to obey the Lie algebra, right? So it's the currents which obey the Lie algebra and not the charges.
Okay, so if there are no further questions, thank you, Sreerup, for a very nice and simple lecture.
Yes.
And I guess
Thanks,
part 2
Professor
will be more
Suresh,
fun.
for coming to chair also.
What?
Thanks also for chairing this session from Germany.
Okay, thank you.
Where are you in, Suresh? You're in
Oh,
Germany?
Italy, sorry.
You're in Italy?
I'm in Italy.
Okay. Okay, then buonasera.
Okay, bye. It's my
Okay.
lunchtime. Bye.
Oh, I see. Okay.
Can you please share the
So-
slides of your talk with us also?
Yes, I will share. I will
Yeah.
share. I'll send them to Devendra. I think he will
Yeah,
take
yeah.
care.
Thank you.
Okay, I will. Will you be there next day also, Suresh?
No, he left actually.
Will you be there next day? Anyway,
He left the meeting actually, yeah.
yeah. Okay, okay, fine. All right. So next day it will be non-abelian theory. So
Next Thursday.
next Thursday. That's fine.
Okay, sir.
Okay then. Goodbye,
Bye.
everyone.
Bye.
Thank you. Thank you.
Bye.